Hello, everyone. Welcome to Embedded. It is just us this week. And by that, I mean myself, Elecia White, and my co-host, Christopher White.
Hello.
There were lots of announcements last week.
There were? I guess there were.
There
were several announcements.
Let's start with the contest winners, since I can announce those.
We're all winners. Except for the people who didn't win.
Well, I mean, they're winning books, which is really nice. But anybody out there who needs a book to read, there's this thing called the library. I highly recommend them.
Who won and why?
Cyril got within one number of my -8. Will was the closest to Bob's 17. And he will be winning Every Anxious Wave by Bob's ex-wife, which did actually sound like a pretty good book. Cyril will be winning Atomic Accidents from Bob again. Roy guessed your perfect number of 496, like right after you said the words perfect. So he'll be getting Safeware. And Adam Grant will be getting Earthquake Storms because John Lehman did not choose 42, despite the whole don't panic thing. He chose the coefficient of friction for everybody who is not in his lab, which is 0.6. And Nick the Exploding Lemur, will be getting Soul of a New Machine, because while his number of 32,768 is not the same as Christopher's 128, it is clearly the closest in spirit.
All right.
There were too many things near that, but nothing really close. Okay, so those are the books. Those are the announcements. Thank you, Bob. Thank you, John, for giving away books. That's awesome.
Thank you for everyone who sent us funny numbers.
Yes, I did. I learned new numbers. It's weird.
You know, you can learn new numbers just all day long.
1003, 1004.
Well, those aren't new. Just keep adding one for a while and you'll get there.
Eventually, yes. But no, there were interesting numbers, and somebody did guess E plus I. And I will have you know, Warren, that I did take the magnitude of that in order to see if it was closest to any of the numbers.
That's very kind. You shouldn't have done that. But next time we should specify,
No imaginary numbers.
Only reals.
Only reals, yeah. Rational.
Or only non-reals.
We'll see. So, done with that contest, moving on to another one.
What? It's just contests forever.
I know, it's kind of odd, but kind of cool. I get to give stuff away.
What are we giving away now?
Well, this is the Embed has their conference in Santa Clara. It's the Connect conference. It's a day long. Embed is awesome. Here's how you use what we do, and here are our boards, and just welcome to Embed sort of conference.
And Embed, for those who are joining us late.
Embed is a branch of ARM, the processor IP vendors, and they...
You mean SoftBank?
Man.
Sorry.
Right. SoftBank bought ARM, but I'm just going to ignore that. And Embed is a compiler that's online, and they qualify different boards to work with their compiler.
C++ compiler.
It is a C++ compiler. They have a huge library and community of various people doing drivers, so it's a good place to start. If you want to, have an accelerometer and some buttons and some lights, and you go to Embed and you get your core processor that's a STM or an NXP processor, and then you...
NXP about to be bought by Qualcomm.
I can't keep up. And then you put it all together on Embed, and there's lots of existing stuff out there.
So we kind of recommend that for kind of the next baby step up from Arduino usually, right?
Yeah, it's not quite a baby step. It's a bit of a hike, but it's a definite
a toddler step.
Yeah.
The preteen step.
And they're going to unveil some of their test-driven development. No. Yes.
Unit tests.
Unit tests.
Which could be used for test-driven development.
At their conference. And their conference is in Santa Clara on the 24th of October. And we do plan on going, Christopher and myself. And it's $25 if you want to go. But if you email me, I don't know. Christopher wanted a screenshot of your iTunes review.
That was a joke.
Oh, okay. But just let's say the first 5 people to email me. They gave me a couple more than that. So if you're late, you can still get in with the sob story. But let's just go with the first 5. I want you to say, I'm going to be in Santa Clara on the 24th, and I'll happily give you the code. Okay. Works? They're okay with you?
Yeah.
You don't want to make them do weird?
No.
Okay. Let's see. I also mentioned last week I'd be speaking at IEEE Computer Science about the tricky parts of embedded. That is October 11th, which is shockingly close to now, given how little I have actually done on this talk.
You're not supposed to reveal these things.
Well, all I have for the rest of our notes is I haven't really started my talk. Christopher, will you give me some advice? Will you do my homework for me?
I gave you a list of the tricky parts.
Yes. Christopher's list of the tricky parts starts with frequent electrocution.
Yep.
How often have you actually been electrocuted as an embedded systems engineer?
I might have forgotten. It often scrambles your short-term memory.
You have, in fact, been...
Could be daily.
Poked by needles of uncertain origin, which was an adventure that was terrifying for a little while.
That wasn't really the embedded system's fault.
Well, if you'd been
the embedded system
web
was
software
on
person.
the cart with the needles, so... That was a bad company. Bad company.
Rolled newspaper up and hit it on its nose.
But that would fall under a different category. Electron Gnomes, was the other one?
Yes, Electron Gnomes, which I definitely am going to talk about in my presentation, although maybe not as that. Maybe I will talk more about the difficulty of debugging systems.
That would be gremlins. They're totally different.
Oh, really? Yeah. What are Electron Gnomes?
They're gnomes that are made of electrons.
Schmebulak, could you be more specific?
No, I just made that up before. You expect me to have a backstory?
Yes.
That's not how this works.
You've had days to think of this backstory. Well, I am going to...
They're gnomes that steal your electrons.
And then your power sags.
And then question mark, and then they profit.
Yeah. Well, I am going to talk about the difficulty of debugging embedded systems and the wonky cosmic ray sorts of bugs. And
no, you're getting into real details now. We can't intermix this. This is the entirety of the notes?
Well, yeah, I want you to write my talk. I thought you understood.
This is the shortest set of social notes we've ever had.
Because I have to give an hour-long talk.
Well, let's move on to the rest of the list, because we obviously need to fill time.
Well, no, Electron Gnomes.
Yeah?
Or I'm going to pretend they're gremlins. Okay. I'm sorry that you have a differentiation. I just don't.
No, that's fine.
Reverse time anomalies, which I believe Andre covered in his blog post last week.
Sure.
Did you have anything else to talk about?
No.
So reverse time anomalies, I think I'm actually going to use Christopher's list as my outline. So if you come to the talk, you may see me making fun of him or him throwing pizza at me. You never can be sure.
Or both. Next up was glue, which you have to admit is a common problem.
And I was going to talk about glue logic because I have this whole framing idea.
Can I believe you're building real things out of this list? Yeah, I have the whole framing idea. And
I'm going to take I think I've chosen a Nordic processor, a BLE processor, and WS2812s, the little smart LEDs. Mm-hmm. And I'm going to pretend to make an Internet of Things thing. And it's going to be a BLE LED. And then I'll discover that quotes, that you really can't do this because the Nordic's operating system doesn't give you the granularity in timing that the LEDs need. So you stick on another processor, a little 18 tiny, that's, tiny and cheap. And now everything becomes so much more complicated because you have another processor to bootload. You have all this glue stuff that before you had pretty simple, turn the LED to blue, turn the LED to red, get it from the BLE and blah, blah, blah. But it's all that glue in between them. And then being able to do firmware downloading and gluing that into the controls. And I don't know.
Well, it's good. If you do BLE, you're going to have to talk about the controller side. The phone, the app.
Yes. Yes, actually, that was number 7 on your list.
Oh, all right. Number 5 was eclectical engineers, which you have to admit is a problem everywhere.
I mean, initially when you wrote that, I thought it was a misspelling for electrical engineers.
No.
So what did you mean by eclectical engineers?
I meant it sounds like electrical engineers, so it's funny.
Okay, and so to make this as part of my talk, I'm going to have to talk about how an embedded system engineer has to be interdisciplinary. Yeah. You have to be a software engineer. You have to be an electrical engineer. You have to be able to talk to the mechanical engineers because could you please move that bolt from where my serial port plugs in? And so I guess eclectical engineer, all right, well, we'll keep that.
Memorization of the liturgy.
That one's easy. I mean, that was actually in my outline before you suggested it. Because...
in those words.
Well, no, I had acronymphobia. But we go through so many of these stupid K60FN1 XX12. And why in the world do I need to remember all of those numbers and letters together? Can't we just call them like stupid USB processor? Wait, no.
That's good marketing. I don't think that's going to work. No, inside companies, they probably have memorable code names, but once they get productized, they're,
I mean, I know that one is named the way it is because it's in a family. And I have learned that the K60 of this particular variant is closer to the K60, to the K70 than to the other K60s. And so I have this one that's sort of an anomaly. And I understand how that happens when you set up the parametric chart and you go here and here and here, and it all works out so that you get these sets of letters. It's the best description. It's a thorough description. But man, I hate remembering them.
But it's only a thorough description to somebody who's familiar with that part. And you have to remember everybody's scheme. So that's silly. Well,
and you mentioned that SoftBank bought ARM, and that hasn't changed anything for anybody yet.
No. And it won't.
I really needed to know that NXP had bought Freescale because half of my documentation was, or my documentation was all in NXP now, but half of the forum information was still Freescale. So I had to, you do have to memorize the liturgy. You have to remember what's going on in your processor and your processor's family and all of your sensors and their families. I mean, they say that engineers are isolated, but we have lots of families we're talking to all the time. No, I don't know if that was working. Number 7.
4% chance of decapitation.
Okay, this one's going to start with a story, I think. Is that okay with you?
You can do whatever you want.
So I heard somewhere that in a survey that 4% of respondents said they had been decapitated. And I found this an amusing example of how surveys are stupid and how they just don't give as precise information as we give them credit for giving. And so I told Chris this. Hey, honey, did you know survey respondents, 4% decapitation?
Well, I'd already seen the survey, so I was prepared for this conversation.
Oh, I see. You were yanking my chain.
Of course.
With forethought.
Of course.
I did not know that. And Chris says, decapitation is a medical term. It doesn't mean that your head is rolling on the floor. And,
you took affront to this.
We had some discussions about what percentage of the population had been medically decapitated and were still able to respond to surveys.
There's an upper bound.
And
it's no higher than 4%.
And eventually I said this was the lamest well actually I had heard in a long time.
Which it was not, I pointed out.
Because he had used neither the words nor actually. And well actually, a well actually is defined having used the words well and actually.
I managed to meta well actually you.
Yeah. Yeah.
I don't see why you don't appreciate this.
I must appreciate it. I told the story.
I think you're just trying to humiliate me. And that was all I had on the very quickly thrown together list. When you asked me this question to do your homework for you. And I took it seriously, of course.
I'm not sure you took it seriously. So I don't have an actual place to put the 4% chance of decapitation unless I don't know how to fit that into my tricky parts of embedded talk.
You'll come up with something. You've got a week.
Oh my God, I've only got a week. That's terrible. Thanks for that. I am supposed to talk about processor profiling, map files, bootloaders, and debugging remotely. I know that because I wrote an abstract long before I started the slides. So,
it's a really large set of large topics to go through in an hour.
Well, I was going to talk fast.
Yeah. I noticed one thing you don't have in here, despite number 3 on the list, is anything about timing. Time is hard.
You mean calendar dates?
Both.
Yeah.
So if you're doing a control system in real-time stuff, that's difficult. We talked about bit banging. That's a timing thing. That can be difficult. But then calendar time is always a nightmare if you have anything you need to have a real-time clock for. And if it's an actual product that needs to be used anywhere in the world, that gets even more difficult.
Well, the precision timers can go in when I talk about how you have to add a processor for the LED control, because you have an RTOS, and while R and T stand for real time in the operating system, that just means you have a consistent response, not that you have a fine-grained response.
And if you wanted to talk about the calendar time stuff, you could bring up the old holiday configuration scheme for the light or something like that.
Oh, right. I could do that.
See? Oh, what?
You should describe what it was.
Oh, that was your scheme years ago to make Christmas lights. Well, not Christmas lights, but holiday lights that you just put up once. And then they know they have an internal calendar, and they had color-changing LEDs, and they knew what holiday it was. So they would automatically change to red and green or blinking for Christmas.
I had this cute
bright
little
green
story
for Arbor Day, brown for Thanksgiving.
How you came home and you knew it was Valentine's Day was coming because your house was starting to pink.
Right. Yeah. Except LEDs were slightly too expensive to do that with.
Oh, it wasn't that. It was the control system.
Yeah.
It was before the WS2812s. This was like 2006 I was working on this. And I was looking at PWMing LEDs in bundles of 8.
Oh, right.
And so you had 24 wires going through the cable.
What a nightmare.
And not counting ground. And it was just not tenable to build and organize and keep running.
And then somebody came out with it a few years later.
Yeah.
But it wasn't
GE
like
lights.
It wasn't hooked into the calendar. It was just you could choose like some subset of things. I think you actually hacked that up, right? Didn't you give a talk where you took that and hacked it so it could do what you originally wanted?
I did. I hooked it to a Wi-Fi board.
Right.
And I didn't do the original hacking on it. Deep Dark did. I think that was who it was. But those were, he used a logic analyzer and just looked at what the protocol was and wrote it up and did a beautiful job. And sometimes when I'm looking at Hackaday stuff and thinking about what I want to write, I think about that. I want to write something like that because it was useful to so many people. It wasn't just me and my silly holiday lighting idea. All right. So yes, calendar is horrible. Precision timing is horrible. What else did I miss?
Well, I mean, you have the obvious things listed, right? I'm trying to think of the non-obvious things, or the things that somebody who's an experienced engineer who maybe comes across an embedded project for the first time doesn't realize. I mean, one of the things I think of is the speed of iteration can be very slow because either you have to download to Flash, or you have tools that are very slow, or your processor is not very fast, or, the deployment of new code takes a long time, where a long time is anywhere from 5 to 10 minutes. That's a lot different than standard kind of engineering practice where you have an application and you can compile it and it maybe takes 30 seconds to compile, and then you restart it and you find a bug, and you can iterate really, really quickly that way.
Well, then when you do test-driven development, you have to decide whether you're doing it on the target processor, knowing it will be slow to deal with,
Sure.
or if you're doing it offline, which will be faster to compile, but may have problems when you don't have the same or you don't have the same int size. Or
not even the same tool set. I mean, a lot of times you might use GNU tools for your unit tests to compile, and you might use an embedded tool set, embedded compiler for your device. So you get into other issues there too. But that's a little corollary to the original problem, which is things are slower. And so it kind of gets back to that, development habits of being much more careful. Because if you can iterate really quickly, you kind of fall into the trap of, well, I don't have to really think about this because I can just try. If I have a particular bug I'm trying to solve that might have, it might be some combination or order of code. If you can iterate really quickly, you're always tempted to just try every option until you find the one that works without maybe understanding the actual problem and solving it through thought.
Yeah, I've been working on a command parser, and I have to admit, to do the checksum, I read the description and I thought, I'm not going to get that right on the first try. It's not hard, but there are like 4 ways I could implement that. Let's just try them all.
Yeah. And sometimes that's fine, but I think it's not necessarily a bad thing to have something external forcing you to slow down a little bit. And so I guess that's the other side of the slow deployment and test cycle time, is that maybe you should think a little harder. I don't know if you want to talk about that, but something that came to mind. I'm trying to think of what else is difficult that maybe isn't obvious. Dealing with actual hardware instead of an amorphous computer or a server somewhere.
Well, I do want to talk about the protons in the electronics, that while you may start with an off-the-shelf dev kit and you may connect it together and it all comes together fairly easily, when you have a custom board, it's hard to debug because you don't have all of the signals going from one place to another. You can't look at them anymore. They're all on the board, and if you've miniaturized the board, they don't come out necessarily.
Can't do that in a computer either.
You can have variables you can watch.
Oh, I see what you're saying. So your visibility into the software isn't as good as, yeah, right. And a lot of with JTAG debuggers and things, you're limited to a handful of breakpoints, maybe one breakpoint, depending on the processor and the tools, right? And maybe even less in terms of watches. So that's another limitation, but that's part of the debug thing, right?
Yeah. I am going to talk about the difficulty of debugging.
But what I was talking about with hardware is just you actually have a physical thing that you can ruin.
Oh, the cost of actually being offline for maybe a long time because you only built 10 prototypes and now you've trashed 9 of them.
Well, it depends on who you is, but just as an embedded software developer, you have a bare board on your desk. It's not the same as a computer. There are ways you can, depending on how it's designed, there are probably ways you can, through software, ruin it.
Those
if you have
darn flash.
Right. If you have a flash system and bootloader that's maybe not quite robust, you can break a system, which requires, an electrical engineer with a soldering iron or somebody with different access to fix. But it's different from developing applications or anything else because you can't really break a computer with your software. And the consequences of being wrong, of dumping your coffee on your board or which is bare and on your desk is higher, especially if it's something custom, right, where you've made 10.
That those few initial prototypes are so expensive.
Right.
And so people don't order 1,000 of them unless they're a big company or this is a minor iteration. And those board costs have come down a lot, but it still
costs you time.
It's still a lot of time, and it's still a lot of people. I don't know, when I mess up writing software on my computer, I seldom have to go admit it to somebody else.
The flip side of that is when somebody designs a board, if it's a non-form factor board designed for development, there are ways to make it not ergonomic, so you're more likely to break it. I'm not looking at anything on my desk right now, but that's a thought process that the electrical engineers sometimes need to put into it. It's like, you can't just throw something together and say, okay, all the parts are there and it's going to work. Here it is to some software engineers who, we aren't necessarily the most careful folk with physical objects. So if you got, boards sticking off at right angles and daughter boards and things, or
when they put all the connectors on one corner of the board and they don't
that's okay.
Key any of them?
That's okay. Having them all arranged, having all the connectors on one side is great.
Well, it's the whole keying thing, because I will absolutely plug it in wrong.
But, if you've got 3 USB connectors and they're on different sides of the board and the cable has to go over something you have to interact with, it's just stuff where you're going to be bending something or touching something, and you really don't want, these are not designed to be robust and banged around. So this is maybe a request for future electrical engineers, but have a little empathy because you're going to be the one fixing it.
Yeah. There are lots of times where I get boards that just aren't designed to be robust, and yet I'm supposed to do extensive testing with it.
I'm still marveling at the hydraulic press thing in your office. I don't really understand that.
I don't think we can talk about that.
Didn't say what it was.
Yeah, it is some sort of manufacturing device that has to do with pogo pins, and it is ginormous. Yeah.
It's the sort of thing usually done with thumb screws.
Well, that project has got plenty of thumb screws, I can tell you that.
All right. Well, what else? What else are you going to talk about? Continue writing your talk for you?
Yes, please.
You didn't tell me this was going to be a lot of work today.
I'm sorry. Sorry. Next week we have a guest. I will just make him talk the whole time. In fact, if you want to go kayaking before or during, we can do that.
Don't think that's going to work.
No. Last I heard, you wanted to go listen to a blues show while we were recording.
Not possible. What else is hard? It's all hard.
Downloading firmware.
Oh, God.
Is just one of those things that when you make your proof of concept and then you want to get from your proof of concept to a shipping product, the downloading firmware box ends up being such a stumbling block for so many people.
Well, it's difficult. And it depends on your flash architecture.
And on your
and how
security.
You've laid out the bootloader.
And the bootloader.
If you've just done a proof of concept, you may not have thought about any of those things.
No, because, it worked. It had all of the functionality we said we wanted. It lit up when I did BLE stuff. So therefore, we're ready to ship, except you're not. You have this huge bootloader thing that can brick things. And if you have multiple processors, how do you download for the secondary processor? And it's a mess. So I was actually gonna take some from my book for diagrams of different bootloaders.
Has anything changed since then?
Well, the Nordic system, when I last used it, they had lots of features to make downloading bootloader, or they had a built-in bootloader that made downloading firmware a little easier. And they used a ping pong method, so it was pretty tough to brick your system. And that's good. But then it did take a lot of space. And so many people are using the free Kyle compiler that is space limited. And so if you do that, then you have to make sure you have all of the space in the right parts, and you have to understand how to put Flash together so that you can have multiple programs in the same Flash that don't count against your compiler, because compilers are huge and they're dumb and they're expensive.
They're not all expensive.
No, but the reason I use the Kyle, the reason I recommend using the Kyle with the Nordic is because that's where all of the sample code is.
Right.
And it is more expensive to port everything to your personal favorite compiler than it is to get used to that one. I know somebody's going to point me to Embed actually has a nice Nordic system, and yet I still use Kyle if I'm doing it professionally. And I know there's a GCC version, but I feel like Nordic and Kyle work together, and as part of the liturgy memorization, if I know that, then it makes my life simpler.
Yeah. I'm just having bad memories of Kyle.
I don't get attached to them.
You don't get attached to them?
Well, I mean, I don't.
I haven't gotten attached to any of them. That's true.
Yeah. Other that whole sample thing, I want to inject, pretend, I don't know, talk about, let's say you get a bug in the downloader. Now you have to decide. Now you say, oh, well, Nordic has an update and it does what I want. It's better. But then you go and they've updated all the files, all the interfaces. And do you update everything? Do you update your code to the latest, which may have new bugs? Or do you stay where you are and live without this feature you wanted? This SDK and sample changes, and they don't necessarily have versions. And this isn't just Nordic. I don't mean to slag Nordic. They do a fine job. As good as anybody does. This happens with TI. It happens with everybody. The Freescale thing, or the NXP K60, whatever, they changed the USB library, and they didn't change all of their examples. They only changed some of their examples, and it was awful. And yet that is something that I don't know if other software engineers have to deal with, but it is really common in embedded systems.
Usually no. I mean, the types of things you're piecing together for applications, say, are either system libraries and things, and those are carefully versioned, and they'll have the care to deprecate functions but still leave them operable for like 2 major revisions or something. And of course, all the examples are usually updated much more comprehensively than that sounds like is being done for those things. I think it's a much less common problem. I mean, it does happen. Well,
I mean, there's Python 2.
The 3.0 thing,
3.
Yeah. But that's kind of the example that
everybody points to and says, "Don't do that."
Yeah. But I'm thinking about like Qt, which I'm not going to call Qt. Sorry. They made a major revision breaking thing a couple of years back. But they do a good job of documenting, transition. Like, this is how you transition your code to the new system and the new APIs. They continue to support the older one. It's not like a situation where you can't. I mean, they do have features that you want to grab from the new one. So if you're compelled to move to a new feature because of that, but it's not like they've come out with new hardware, and if you want to upgrade your system to that hardware, now you have to rewrite all your software. So that situation doesn't happen as much. I think it's a problem, but I think it's much less of a problem because I think the embedded hardware companies, their goal is to sell the chips.
We should be happy they give us sample code.
Yeah.
I mean, that's actually a pretty new thing.
Yeah. It's a better situation than it was, I think. Seriously,
if you're going to give me sample code of a UART driver, can't you include an interrupt?
Well, that's the other thing. And tangentially, I was going to bring this up. You know, somebody coming into embedded engineering might be surprised at how much reinventing the wheel we have to do with every project. And it's kind of painful, and I wish it would go away.
Oh, yeah.
But if you're coming from, if you learned modern development recently, you tend to piece things together from other people's frameworks, and there's a lot of stuff available depending on what language you're writing in and what target. There's a lot of stuff where you can just say, oh, I need this library to do this kind of thing, or there's this, container or object that does this kind of database for me. So it's really more of a architectural problem than a tactical coding problem a lot of times. And with embedded, it's still very much a tactical coding problem where often you start a new project and it's, well, here's my blank slate. And all right, I need a UART driver. I mean, certainly if you're developing on Mbed or Arduino or, a platform that's got a community surrounding it, that tends to be better. But I think if you're coming at something from a custom build point of view, which still is a lot of professional development, there's, pieces missing that you've got to code yourself. And you may find yourself getting something that's maybe not perfectly suited to your needs, like a real-time operating system. You might say, okay, this is good, but I need, this messaging primitive doesn't work quite the way I want, or this interlock mechanism or whatever. And you end up having to build wrappers around your own. And I mean, that happens, all kinds of development, but I feel like it happens more still with embedded where, oh, I have to do a linked list. Well, I'm going to write yet another container, linked list storage class or whatever you want to call it in C. I think we're still doing that a lot, and that's painful and costs a lot of money.
Painful.
But, UART, circular buffers, serial drivers, SPI drivers. I mean, that stuff's all getting written from scratch still in a lot of projects.
In a lot of projects, there are a lot more samples than there used to be.
Yeah.
But they never quite do what you want. And so
And
if the code is not well written, then it is easier to rewrite than it is to read.
And the samples are usually the baseline functionality. It's not going to be necessarily low power. It's not going to be less necessarily high performance.
They didn't even use the FIFOs, man.
Right. That's what I was about to say.
Built-in FIFOs. They didn't even bother.
That's about what I was about to say. Your chip might have, special peripheral features, special DMA modes, other ways to do memory transfer. And a lot of times the sample code doesn't take advantage of that. So you've got to take their sample code and spruce it up. And that, I think, doesn't happen as much in other development worlds where it's like, okay, we're trying to make the library, the software is the product in normal application development. So somebody making you a library, that's their job. They're making a library and they want it to be as comprehensive as possible. Whereas a chip vendor is like, well, here's how you get started. We assume that you're a professional engineer and have written many drivers. So, this is where you start. And if you want it to actually do what you want, you might have to add something.
Well, and so this is definitely, I'm going to talk about this because this is very much on the way of, I built this thing out of off-the-shelf parts.
You built the city on rock and roll? Oh.
And then, but the difference between it working and that proof of concept and actually shipping a product, there are all of these gnarly little tricky things there. And that's what I want to talk about.
There's always like minor stuff, right? You might have something out of the box that works for some configurations. But let's say you've got software and you've got a display driver, and turns out you want the display to be 90 degrees or upside down. Well, now you got to dig in and actually fix the display driver or rewrite it or what have you. So that's where, your physical things in the embedded world can impact your software in ways that maybe doesn't happen in other sorts of development. It's not like anybody comes up and says, well, we want for this application for the monitor to be rotated slightly.
Well, and if they did, it would be part of the computer. It'd be a driver. It would be trivial. It wouldn't be, oh, let me recalculate how I'm displaying things and change all of my bitmaps to be turned or, so part of my talk is going to be about map files, but I actually think that's one of the ways that embedded systems are less tricky than people think they are. So when you run out of RAM or you run out of flash space, there's a file that tells you what everything uses. And if you know about that file, it suddenly becomes much easier to find out where all of your RAM went. And since you're on an embedded system, RAM is a fixed and precious resource, depending on your system. And so being able to read a map file, or just not being afraid of going in there and trying to puzzle it out, is so worth it. And yet I still meet people who, they get lost at that point. They get frozen, almost in fear. And no, this part isn't the tricky part. I can tell you where your RAM went. And I love map files. But it's not something that they necessarily tell you about when you're learning software development.
Not anymore.
I know, not anymore.
I mean, there were different kinds of intermediate outputs and things. I remember before, but yeah. Well, I mean, you kind of buried the lead there too, because somebody coming from another development discipline is like, "What do you mean I can run out of RAM?"
Well, yes, jeez. What do you mean I have unlimited RAM?
What are you talking about? What's this K behind the number of things I have RAM of?
Yes. And then I do want to talk about profiling, but I'm a little hesitant about that.
I would be interested to hear what you have to say, because I haven't had a lot of success with profiling tools. So I always fall back to doing stuff by hand.
I think I actually, in my rough draft of my slide here, I have something about you end up looking at how much the profiling tools cost, and you say, oh, well, never mind, I'll do it myself. And then 6 months later, you look at how much money it took you to build them yourself.
Sometimes. Depends on what you need. Most of the time, all you need is to time certain sections of code.
Yes, and that isn't very hard. I mean, making a little timer system, and then you run it over this command, and then you print out or store or log or however you're getting your information. And you say, okay, this part took 1 millisecond, this part took 40 milliseconds, and then you optimize the 40 millisecond part.
If you're smart.
Well, if you have any cycles to take out of there.
Right.
And then the other profiler way, the way that usually is if you are buying profiling, is to have a random timer tick. And for every timer tick, take sample the program counter before your interrupt. And then you get a view.
You get a statistical sampling.
Yes.
Of where you spend most time.
Yes.
That's interesting. That depends on having enough samples, right?
Yeah, you need to have a pretty big buffer. And then you probably need a program to take your map file and this buffer of addresses and tell you which functions you're in.
Yeah.
Because that's no fun at all.
Right. And you have to have enough storage to log meaningful amounts. But no, I like that idea. I think somebody did that recently.
I mean, there's lots of ways.
Yeah.
There's lots of people who have done that.
No, I know. I was just remembering recently that I came across that and it was cool. Yeah, and those are things you can do yourself.
Yeah. I mean, the statistical sampling one, you do kind of have to commit to writing the interrupt, trying to figure out what random means for your system. And then you're still not sampling anything that has interrupts turned off. And so you have to be aware of that. And you do have to have that post-processing output where you merge with the map file, which, I mean, I would write it in Python. There are map file readers in Python now. And it's not that hard, but you're not talking about an hour's worth of work.
Yeah. And in other situations, you may find yourself needing to flip a GPIO and time stuff on a scope. I've done that a bunch of times too.
Yes. And you know what? I forgot to put that in these notes.
And that tends to be, if you need super accurate timing because you're doing, oftentimes when you're profiling stuff, you think, oh, well, I'm just going to find out, that this operation took find the, like you said, find the thing that takes the longest time and optimize that. But maybe the thing that takes the longest time is composed of 50 different small time things, and you need to see how often you're in one of those. And so it's not that you're going to get, one 100 millisecond long operation, but you're going to get something composed of hundreds of microsecond or 100 microsecond long things, and those you got to dig into a little more. So sometimes you have to use a scope for that.
Yes. And using a scope or a logic analyzer is important. And that's a tricky part that I don't know how to explain, because as a newer engineer, it took me a while to understand that sometimes I had to acknowledge I wasn't going to figure this out by typing at it. And I really needed to spend the 2 hours or whatever to hook up the scope and get the capture. And then it would be a 5-minute solution. But it's hard to agree to that upfront cost.
Yeah. Well, and it's realizing that you're blind, right? It's realizing there's some state of the system that's either too fast or that you have no visibility in, or it's controlled by hardware, that you need some extra external tool to reveal to you. And that doesn't happen much in application development because you've got visibility into everything the OS provides you. Hooks for tracing, and more modern OSs even have really, really complicated tracing capabilities that give you all sorts of timing information about what function you're in, what line's happening. But if you've got a SPI bus that's not working, or if you've got something else that's interacting with signals, you can't see that from software.
Or you don't realize that it's your printf function that is using a stupid UART that is polling for when it can send bytes, and it's making your whole system incredibly slow because it's doing everything the dumb way. And when you start out with your proof of concept, you don't care that it's going slow. You're not trying to save power. You're not trying to make things go fast.
So okay, we can get off profiling, I think, but power.
One of the things that I want to talk about with power is you shouldn't try to optimize things you can't measure.
Oh.
And so you need to understand how to measure power, and it's not always easy. Low power things are the hardest things to measure.
I think that's the trickiest thing is dealing with trying to optimize power. Of all of the things, that is like masterclass advanced.
So do you mean the difference between sleep and hibernate and super low power?
Getting sleep states right, measuring to prove that you're actually doing what you think you're doing. Finding where you're burning the most power in your code.
And figuring out if that's where you should be. I mean, if this is the purpose of your device, then, if I have my LEDs and my LEDs are on, I don't necessarily need to optimize my processor to take no power because my LEDs are burning everything. It's one of those instances where you should only optimize when you need to.
Yeah, but that tends to be a product-breaking optimization, right? If you're battery powered, you have to work on this because either you're going to be constrained by form factor, what size battery you can put in, or there's some requirement that this must last for this long.
But don't optimize the use case. Don't optimize the LED on case. Optimize the sleep case. Because if you're
optimize
off
something for the LED on case. You have to optimize battery. I mean, optimize doesn't mean making as small as possible. It means getting things right.
Okay.
So you may have to say, oh, my LED needs to be on, and that's driving all the power, and there's no way I can change that. So that means I need to go to a battery that's X amount bigger than I anticipated.
Oh, okay. I see where you're going. I was going more with your battery's fixed size when you are looking at which states to optimize. Trying to optimize your short amount of actual runtime to be even shorter is not as important as making sure your GPIOs are in a low power state when you're in a deep sleep. Because it's the deep sleep you spend 95% of your time in. And so you want to figure out where it is important to optimize. And again, that means you have to be able to measure it. Measuring things like nanoamps is a pain in the neck.
Well, and then there's the counterintuitive parts of optimization where you sometimes have knobs on your processor that could slow it down, for example. So,
Yeah.
I can save a lot of power if I run this at 1 megahertz instead of 12 or 48. And so you turn things down as often as possible, but then it doesn't save you power. And the reason might be because it's taking a long time to do something that normally it would only be awake for a short time for. So you're at 1 megahertz, so you spend, let's say you have a difference between low power and high power of 1 megahertz or 12 megahertz. So at 1 megahertz, it takes 12 times as long to execute some code. Well, you're out of sleep for 12 times as long. And so it's actually better to stay in the high-powered state when you're awake to get your stuff done and get back to sleep as quickly as possible.
And so these are all features with ramifications, and you have to think about all of the ramifications. You don't necessarily want to go to sleep if you're going to wake up a cycle later, because there's an expense to going to sleep and an expense to waking up. And it's not instantaneous, and so it takes power. Weirdly, you have to balance whether or not you should even bother to go to sleep.
Well, or if you have a badly designed system from a software point of view, you might have just random events happening unpredictably. And you might wake up for one and then go to sleep and then immediately wake up for another, like you were saying, and just have them distributed through time kind of evenly. And so you're actually awake quite a lot of the time. And spending that fixed cost you're mentioning of powering up and powering down, you're doing very, very often. So you've wasted a lot of power just waking up and going back to sleep. But if going back to the time thing, if you consider how to bundle all those operations and say, okay, I'm going to wake up every 10 milliseconds and do everything that's been, that was waiting, and then go back to sleep. That's a lot better because now you've reduced that state change to just a few times rather than constantly doing it anytime something happens.
And so you end up not turning the interrupt on. You turn the interrupt off, and instead you wake up on a timer and you poll the system. Yeah. Which
it's counterintuitive.
Is so counterintuitive.
Right. This it looks terrible. I mean, from an architectural point of view, it looks very inelegant and sort of stupid. But it's actually the way you optimize power.
And yet, the tricky part of embedded systems is that they are resource constrained, which means you have to optimize for particular resources, whether that's battery and power or cycles and power or cycles because you just don't have enough, or RAM or flash. I think that and remote debugging are the two really hard things. People don't understand about different debugging methods, and it's...
You also haven't lived until you've done remote GDB. Have you done remote GDB?
Yeah, but... Yeah.
Your telnet server to your device?
Well, let's see. Other things I have in my list are the non-embedded software parts, or the non-embedded parts of your project. There's the mobile app, which... If you did your proof of concept, your mobile app might have been one of those BLE interface things like light blue, which just toggles characteristics and isn't pretty. But if you're shipping a product, working with that mobile app to get it right, to let it do firmware updates, to let it have reasonable security, that's all stuff you may not be able to control. And that is really tricky. And the website, if there's a big cloud website, and security, and making sure the security goes all the way through the system to your part. The hardware is, of course, tricky because you shouldn't dump coffee on it. And then manufacturing tests. People don't seem to realize that that's part of the embedded software job. You have to... I
don't think they don't realize it. I think they don't want it to be.
Well, there is some of that. But if you can make your manufacturing tests and your board bring-up tests, if you think about them at the same time, it may be easier. And you do have to do the board bring-up tests. You don't really get a choice on that unless you want your boards to be untested when the hardware engineer gives them to you. Which, dear hardware engineer, if you haven't tested the power system on your board, I don't want it. Oh, sorry. That was... sorry. I should just put that in email. Okay, anyway. Manufacturing tests. It's one of those things that when you go from a proof of concept to a shipping product, you can't forget that. And there's not anything truly tricky about it.
Oh, yeah?
Other than the existence.
Takes up a bunch of space that you may not have.
Well, or you have to do a firmware update in in the factory.
Yeah.
I was going to talk a little bit about factory firmware update because that's odd, but you've given me so many other ideas that I may ditch that part. I'm glad I didn't put very much in my abstract because that means I can change it all.
You haven't written any of this down. You're just going to listen back to the podcast.
I totally am just going to listen back to the podcast. I hate to listen to my own voice, but still I can manage.
That's all right. I'll change it.
Oh, can I be Darth Vader?
Sure.
Oh, excellent. So yeah, that's my talk.
We missed anything?
We haven't missed anything on my list or on yours.
Environmental?
I used to have more problems with environmental, but lately it seems like the processor vendors are a little more aware of that.
Oh, that's boring.
Yeah, it is sort of boring. The TI BLE chip I used recently, this goes back to the stupid memorization, CC2640.
Sure.
Had this whole press to test mode or something, PTM, and it did all the FCC testing for you.
What?
My software, all it had to do was recognize that button was pressed and call the function, and it went off and did something and it worked. I mean, that was how we did. It was so weird.
No, now you have to explain because that doesn't make any sense. To do FCC testing, you have to do it in a chamber with.
Oh no!
Oh, it just triggered.
But I didn't have to write any special software because
got it. It wasn't just
squawked as loud as it
magically
could.
qualifying itself.
No,
That's what I thought you were saying.
No, it was just that my embedded software didn't have to do.
Got it. Yeah. Okay. That's fun if you've never done that though. Go and do FCC testing. It's kind of cool.
It's interesting.
Yeah.
Makes you want to put everything that's in your pocket in there just to see what's squawking.
Well, I remember you go with, lots of tinfoil and tape and try to put it over things, figure out where, particular things. Emission testing was the one that was the fun part. The other one's where they try to destroy it with what was it? It's emission and what's the other kind? Where they try to zap you? Radiative?
Radiative,
Maybe.
but I thought that was emission.
Yeah. Anyway.
Yeah, when they get out the kilovolt things and start touching your boards and you're like,
don't do that. Yep, doesn't work anymore. Yeah, it's good stuff.
All right, well, that's my talk. You all are, of course, invited. It is October 11th. If you come, do ask for a sticker, just so I know that you're there. I'll be giving stickers out ahead of time, probably before too. And it's free. Maybe I should qualify that. Oh, that they're providing pizza, so it's not free. It's like $7. And there's a Eventbrite thing. So, oh wait, it is free. It is free. So you can have pizza too and hear me talk.
Wow,
it's like two for the price of free. But if you can't be there, there will be a webcast. Really? There'll be a webcast? Crap.
You're just learning this now as you read this? This is fantastic. Also, did you know that you will be on live television and simulcast into theaters across the country?
Yeah, I hope not. And I do plan on putting the talk on YouTube, so we will figure that out. It may go on the IEEE channel, or it may go on mine, or it may go on both. We'll see. It'll be exciting. And if you aren't into videos, this will, of course, eventually become a blog series. Because if I'm going to do all this work of writing it and figuring it out and making interesting pictures to go along with it, remember, we have to go get milkshakes because I need that for the firmware download picture. Yeah, so it will be on the blog. Which reminds me, Andre is like really getting into the STM32 discovery board and breaking it down. And Chris Vec has gotten a little busy, so now he's posting every other week, but he's still on the 420, MSP 420 from TI and talking about the underlying microcontrollers. So you get two different perspectives on our blog right now. And I'm just in random put up whatever makes sense this week mode.
SP 420.
430.
Okay, good.
430.
Because that's a non-contact ultrasonic level transmitter. MSP 420.
How do you say that word?
The Polysonics MSP 420 non-contact ultrasonic level transmitter with built-in 4-digit LED, 26-foot operating range. This is great.
How do you say
liturgical.
that?
Liturgy.
Liturgical? That doesn't sound right. That's like a turtle that's been turned over.
Liturgical. There's a liturgical calendar.
Excellent. Well, yeah, the whole memorization of all of these numbers and letters. I know sometimes I spew them out, but it is just a pain.
Yes, he's been doing the MSP 430 blog series. And you said something about Andre?
Andre's doing the STM32 F4 Discovery series.
Yes.
He's coming at it more from the software top-down side, and Chris Veck is doing a little more on the bottom-ups.
And someday they'll meet.
At some point, they're going to crash into GPIO drivers or maybe UART drivers or DMA. I'm looking forward to it. It'll be hilarious. Let's see. And I posted my Toastmaster talk last week, which was dorky. Let's just go with dorky. But hey, it was something, and I've been pretty busy at work.
I posted nothing.
Look, over in Slack, Christopher has said he wants to be Darth Vader.
No, I was just typing that because that's where we collect the titles.
Oh,
yeah.
All right.
Yeah.
All right.
Yeah, I think we're done.
Oh just no, I have a couple more.
Okay.
Just a couple more.
Just felt like it was a
I know. I was careening. We do request that you give us iTunes reviews or Google Play reviews or whatever reviews on whatever podcast system you use. And if that isn't convenient, I totally get it. I have no idea what my iTunes password is.
It's my iTunes password.
Oh, I know what yours is.
Well, let me share the same.
Oh. All right. I shouldn't say it. Anyway, if reviewing is not convenient, we do have this neat logo that now can be made into a poster. And if you have a coffee shop or maybe a bulletin board at work or a bulletin board at your school in the CS department, if you would print
maybe a billboard along the highway,
that would be cool too. If you print it out and post it, I would very much appreciate it. If you just sit down and talk to someone and say, have you heard this show? It's kind of cool. If you hate the show, you don't have to listen. I absolve you. You can not talk about it to anybody. Why are you still listening? And yes, if you could just talk about the show, it is helpful to us to reach more people. Reaching more people means we have more giveaways.
And more guests.
And it just all works well. And we're still not making money from this unless we have Amazon links in the show notes. And then if you buy stuff, we get like 2%. It's not. Some of you are doing that, for which we thank you, and it does pay for our hosting costs.
Sometimes.
Most months? Every month for the last 3?
Yeah.
Hey, it's cool. I like it. It's going to make my taxes harder. But that is not a complaint. All right. I did not write the whole outro thing, so I'm going to have to wing it.
Wing what?
Do you have any last questions, Christopher? I know that's part of the outro.
I do not have any last questions. Do you have any last thoughts you'd like to leave us with? You also didn't bring down the
Winnie the Pooh
thing, so we have to do that from memory.
Crash. Winnie the Pooh fell down, down, down. If only he hadn't wanted the honey so much. And then Tigger bounced like Tiggers do. All right, I really can't do this from memory, so I'm just going to say thank you. Thank you for listening. We do enjoy hearing from you. I did like the numbers competition. Feel free to let us know if you'll be in Santa Clara and want to go to the Embed conference. And thank you. Yeah, thank you. Thank you to Christopher.
Thank you.
You don't remember the song?
I do, but I'm not going to sing it.
Are you sure?
Yep.
It's pretty funny.
Mm-hmm.
All right. Thank you. Goodbye. Embedded FM is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive any revenue from them. At this time, our sole sponsor remains Logical Elegance.